Tom Mladenov is a young graduate trainee at the European Space Agency and is a member of the OPS-SAT flight control team. His interests include digital signal processing with GNU Radio, aerospace, cognitive radio, cooperative communications, and dynamic spectrum allocation. Please welcome Tom Mladenov.
All right. Good morning, good afternoon, everyone. Thanks for joining. My name is Tom. I'm a YGT Mission Operations Concept Engineer at ESA ESOC in Darmstadt, Germany, and I'll give a presentation on how GNU Radio enabled us to carry out the OPSAT mission. So first I'll begin with 2 slides about OPSAT. What is OPSAT? Why are we doing it? What are we trying to achieve? I'll talk about our UHF link and how we developed a reference implementation in GNU Radio for the community, which consisted of a receiver application, demodulator and decoder, and finally a graphical application that we made available to the community to start to prepare them for receiving OPSAT. I'll follow up with some of our amateur radio outreach, what we have done, what we're still planning on doing, as well as our ground segment and the mission status. And finally, we'll have a conclusion and an outlook at the end of the presentation. All right, so what is OPSAT? So OPSAT is ESA's first 3-unit CubeSat, and it's dedicated to executing hardware and software experiments in low Earth orbit. So the concept of OPSAT is that it's open to the general public, to academia, to startups, to all the way through the large corporations, to basically upload custom software to OPSAT and execute their experiments. We have over 100 companies from 17 different countries registered to carry out experiments. As I said, the spectrum of experimenters range from academia, startups, all the way through the large corporations. We launched on the 18th of December last year from French Guiana as part of the Arianespace Soyuz VS-23 mission. A bit more technical about OPSAT. Let me get my laser pointer out here. Hope you can see that. So this is a picture of naked OPSAT, as we like to call it. So without all the panels, without the solar panels and the body panels, basically. I've broken it down to the spacecraft bus and the payload. So the bus is, of course, everything that's critically required to run the satellite, and the payloads are all the experimental parts. So a large part of OPSAT consists out of commercially off-the-shelf CubeSat components from GomSpace. We are using the AX100 radio and the electronic power system and array conditioning units for the solar cell. So it's a pretty standard configuration nowadays. Our main onboard computer is the Nanomind A3200, which is a VR32 based microcontroller. To be compliant with ESA ground stations, we basically have a CCSDS compliant S-band chain, which consists of a S-band transceiver with a CCSDS telemetry telecommand encoder/decoder, and we actually have the highest uplink and downlink data rate of any ESA spacecraft as of now, with an uplink rate of 256 kilobits per second and a downlink rate of up to 1 megabits per second. And finally, we have a GPS receiver on board. So that's it for the bus. About the payload, so basically where all the experiments will be interfacing with. So this is basically what we make available to the experimenters, which is a high-definition camera, which is on the nadir-facing panel of the spacecraft, so which is normally pointing to Earth. We can also orient the satellite in other directions should an experiment needed for other purposes, of course. We have an advanced IDCS attitude determination control system, which consists of reaction wheels, magnetorquers, and also a star tracker, so that quite precise attitude knowledge can be obtained by the experimenter. We also have an optical receiver, so you can see it here. The aperture is covered at the moment since it was in the lab, since it's a very sensitive photon receiver. But the idea is that we can perform laser uplink experiments. So we can perform experiments that use data transfer via an optical means from ground with a telescope, for example. We also have a software-defined radio on board with the very well-known LMS from Line Microsystems 6002D. The core of the payloads are consistent of two Altera Cyclone 5 system-on-chip modules, which is basically a dual-core ARM Cortex-A9 processor where we run embedded Linux. And finally, we also have an X-band transmitter for high data rate downlink experiments. So about our UHF link, we use Gaussian minimum shift keying at 9.6 kilobaud at a center frequency of 437.2 megahertz. The protocol in use is the CubeSat Space Protocol, or CSP, a link to libcsp here in the bottom if you want to know more. It's basically a very lightweight routing protocol where basically packets of data are attached with a header that allows you to identify where the packet came from, what the priority is, etc. And this packet, so as you can see here, the CSP packet, is it in the mode 6 that we use, is attached with an AX25 header here, where we input all the call sign information to be radio amateur compliant, because we're using a radio amateur spectrum, of course. And then all of this is encapsulated with a HDLC, so high data link control unit. So we have these flags that tell that there's a frame present in this data here. If we take a closer look at the CSP packet, so as I said before, there in this CSP packet there is a header which has which consists information of like where the packet came from which onboard node, because you have to understand on the spacecraft there's within the CSP protocol there is this concept of having nodes. So a node is, for example, either the onboard computer, it could be a power distribution unit. So each unit on board is considered as a node, and this header tells where a particular packet is coming from. Then we have, of course, a payload, which can consist of any arbitrary sequence of bytes, as well as a 4-byte CRC and 32 bytes of Reed-Solomon error correction bytes. Now about the actual payload. So it's in the case of OPSAT, it's quite simple. Whenever we're sending to or receiving from the main onboard computer, this payload field consists of CCSDS space packets. We call them SPP, so a space packet protocol. Whenever we're talking to a different node that is not the onboard computer on the spacecraft, either it's the EPS or other subsystems, then this consists of low-level telemetry telecommand packets. Again, if you want more information about the CubeSat Space Protocol, there's a GitHub link here to libcsp. So that's basically broken down the UHF protocol that we use on OPSAT. So we developed, as I said in the beginning, we developed a reference implementation for the community with the sole purpose of providing a starting or reference implementation so that people can get started with developing even their own applications. What I'm about to show you, with some minor modifications, we also integrated into our own ground segment, so we're also relying on these applications for our day-to-day communications to the satellite via UHF. So a simple diagram here, it's broken up into blocks. We have our software-defined radio here, our sampling hardware, whether it's a USRP or RTL-SDR, etc. We capture IQ stream via the GNU Radio application, which is a standalone receiver application, which also uses gpredict as a for Doppler compensation, which I'll talk about in the next slides, how we do that in detail. We obtain a filtered IQ stream, which is then demodulated and decoded and giving us the CSP packets that we then also process in a GUI application that we also developed for the community, which parses all the information and also logs it to disk. So more about the slide. So this is what the receiver application looks like. So it's a simple application in the sense that we have different acquisition devices here. In this case, we just have the recording, which we also provided in our GitHub repository, which I'll link, which I'll link in the presentation. I think it's in the end. or other capture devices, USRPs, UDP sources, etc., from external applications such as GQRX, etc. So we acquire these IQ samples and we set the frequency of the sampling device to our nominal satellite frequency of 437.2 megahertz minus 40 kilohertz. So we're using offset sampling here to make sure that our signal of interest doesn't lie in the 0 hertz baseband spectrum, where often some SDR hardware is showing some IQ offsets basically. So we tune the hardware 40 kilohertz lower so that our signal appears in 40 kilohertz higher in a clean slice of spectrum from the sampling device. Then we use this structure here, as you can see. So it's using gpredict Doppler to basically over a local port receive messages which contain the absolute frequency of the satellite, taking into account the Doppler on UHF. So as I said, our 40 kilohertz offset of before, we just add the Doppler frequency to this, and we use that as the center frequency for the low pass translating FIR filter. So basically, it's common not to retune your hardware unnecessarily. So we keep the hardware tuned at the same frequency, but we just change based on the Doppler frequency. We change the frequency at which we change the center frequency of the low pass filter basically. And then finally we resample to a fixed rate, which is 57.6 kilosamples per second in this case. This is a fixed rate which our other flow graph is also configured with, and we send the filtered IQ stream over a 0MQ publisher sync so that the other flow graph can easily grab those samples. Alright, this is what the demodulator and decoder flow graph looks like. Don't worry, I'll go over it step by step in more detail, but we'll focus first on this part here. So let me get my laser pointer out again. As I said before, so from our receiver flow graph, we acquire the samples via a 0MQ subsource, subscription source in this case. Then we perform, since we're GMSK modulator, we perform a quadrature demodulation with the appropriate gain setting, as said here. We then perform a Gaussian filtering before we do the clock recovery to obtain our symbols that are modulated according to the GMSK signal. And then afterwards a binary slicer is used to convert those soft symbols into hard symbols. So at this point we push them to a virtual sync to be used in the next part. So off to this second part here. We get our hard symbols here, which are then non-return to zero decoded. And since all frames on OPSAT, it's part of our documentation, which I'll also link in the end of the presentation. It's all the symbols have to be descrambled first according to G3RUH scrambling. So that is done here with this descrambler block with the correct settings for G3RUH. And then basically we use a HDLC deframer because, as I said before, we have basically a long sequence of scrambled bytes, but that of course after the descramble are unscrambled, which have these flags here, which indicate where our AX25 frames with our CSP data packets are located. So those frames rather are then used to flag those. So this is what the HDLC deframer does. And after that, of course, you see the arrow change. We end up with a discrete sequence of packets, which are then the remains of this deframed stream here, only containing the AX25 header attached to the CSP frame. So at this point, we have packetized AX25 frames. Okay, So we have our AX25 packets here. So now we're going to this part here, via this virtual source. We check the AX25 address, which you can see here. We then strip the header because it's not needed anymore. We're only interested in the CSP part. So at this point, we convert the PDUs here. So the CSP as a PDU is represented here in the flow graph. We convert back to a text stream with then afterwards 1 bit per byte so that we can do further processing on the CSP frame here. So at this point it goes back into a virtual sync. Alright, then we're at the last part of the flow graph. So remember how we have our CSP packet, and we now convert it back to a stream of a stream that is represented by 1 bit per byte. Okay, so as I said before, at this point we have our CSP frame, which is still scrambled according to CCSDS, scrambling polynomial, which you can see here, which are still represented by 1 bit per byte. Since the CCSDS scrambling is a synchronous one, it has to be done on frame level, which is what we're doing here, because as you recall, this sequence here is obtained from the frames that we extracted from the HDLC deframer block. So we're already working on frame level, so that's why we can use the scrambler here. As you can see here, this is just taken straight from the CCSDS bluebook. The initial state is an all-1 state, so we can see here the seed 255, with the length of 7 being the highest order of the scrambling polynomial -1. So we perform the descrambling here with an additive scrambler because the CCSDS scrambler is a synchronous one, as I mentioned before. We repack our descrambled symbols into bytes and create our high-level PDU again, after which we perform CCSDS Reed-Solomon decoding, which is part of GR satellites. As you remember, we had these 32 bytes of Reed-Solomon error correction bytes, which are then used by this block, which are then stripped off, and again well, this is also printed to the debug output console so that we can see if a frame or what the Reed-Solomon decoding statistics are, how many bytes are being corrected, etc., etc. After that, we actually convert the PDU back to a text stream again and send it off to a 0MQ publisher sync. So this is again in the end what we end up with. We have the CSP packet, which has the header, the payload, and still 4 bytes of CRC 32C there. This sequence I've repeated this snippet here just so you can see how we pass the data to the GUI application. So on the right you can see what it looks like. It's basically the top part is parsing the beacon telemetry according to how it's structured, which is also documented in the repository. And at the bottom we can see timestamping of the packets as well as the header information, which I'll get into more detail soon. Basically, if you have this in your flow graph, then all you need to really include in your client application or whatever it is you're programming is a 0MQ socket configured for subscription with a arbitrary timeout, and then just try to receive data from that socket. More about this header parsing. Yeah, so as you can see here, it's being detected as SPP over CSP. So remember how I said that the payload field, the contents of the payload field are dependent to which unit we're communicating, which in case of the onboard computer, so we see here the source, this is a packet coming from the Nanomind, which is the onboard computer node. In this case, it's a CCSDS SPP space packet protocol type packet, so that's being flagged here. The 4 bytes of CRC are being checked here. This is on the onboard computer level. That we attach the CRC so that we can check it on ground if the frame integrity, is okay. And then we can see various other parameters here, such as the priority, source port, destination port, etc. Again, all these parameters, if you want to have a closer look, they're all covered in the libcsp link on GitHub. All right, so I'll tell you a little bit more about our ground segment at ESOC. So all operations, especially in the beginning of the mission during LEOP, which is the launch and early operations phase, were carried out from the SMILE lab in ESOC, which is a new laboratory environment. So again, SMILE stands for Special Mission Infrastructure Laboratory Environment, which is a highly adaptive laboratory set up to support innovative missions, and OPSAT is the first user of this infrastructure. The main communications terminal that we use is on site, which is a 3.7 meter S-band uplink and downlink and X-band downlink dish with a radome, which is called ESOC1, which is the prime SMILE ground terminal. On site we also have a newly installed ESOC2 antenna, which is only UHF, as you can see, with 2 UHF Yagis to support the operations from the UHF side. As of a long time, the operations are all automated. This is because, due to the sun-synchronous orbit nature of OPSAT, all the passes are in the very early morning and in the very late evening. So there's a heavy use of automation in the mission, because we can't support all passes due to the hour restrictions. The spacecraft mission is currently, of course, due to the COVID pandemic, being performed remotely. So all critical passes that we have to monitor, supervise, and attend live are currently being done remotely through secured access to the mission control system. So this is the OPSAT ground segment on the ESOC side. We also have these are the 2 external stations. So we are also working together with new space companies such as LEAP Space, which we have worked with to establish a station for, especially in the beginning of the mission, for LEOP, so that we had a backup station in case our prime UHF station failed. So this station is located in Ireland, near the city of Cork. And then also industry has supplied us with a ground station, also again for UHF. So these are both UHF stations, which is a TUC one, which is located in Austria on the premises of the Technical University of Graz. This is to give you an idea of the 2 stations I just mentioned. So we had the Cork station I01 and the station in Ireland and the station in Austria here. So this is a plot of all the spacecraft ground track position, latitude and longitude, at the moment that we received a beacon or other telecommand telemetry packets from the satellite. So you can see that the coverage is roughly from 40 degrees west all the way through to 40 degrees east. As regards our UHF coverage, the S-band coverage of our prime ground station in Germany is, of course, roughly between that. So this gives you an idea. We also plotted the measured noise level of the UHF transceiver on board as a telemetry parameter, and you can see that, especially over Central Europe, the background noise on adjacent UHF frequencies is sometimes even in the range of 20 dB higher than, for example, here over the North Atlantic region. And this is also something we definitely saw, which impacted communication with the spacecraft, as communication over the regions where the background noise level was lower, which was much more reliable than over Central Europe, for example. So this is also taken up as a lessons learned. So again, this is just to give a brief view of our UHF coverage with those 2 stations. Right, about our mission status. So as I said in the first slide, we launched on the 18th of December. This is a picture of the launcher at 5:54 Kourou local time. We separated at 14:05 UTC with a couple other CubeSats from CNES. We had a first beacon acquisition by radio amateurs via SatNOX, so in the next slide that is covered. We also closely worked together with the SatNOX team in order to get OPSAT decoding capability via SatNOX, not only for us but also for the amateur radio community. So the first waterfalls that we acquired via SatNOX initially suggested that the spacecraft was slowly tumbling, because we saw a periodicity in the signal strength in those waterfalls. And via the telemetry that we got via SatNOx, we immediately saw that the spacecraft was healthy, the UHF antennas deployed, and we had plenty of power reserve. And again, as mentioned, we also had to take these paths outside of working hours and also make heavy use of automation tools. All right, now about the mission status. So the following units have been commissioned. So the SEP, which is the Satellite Experimental Processing Platform, which is basically the dual core ARM Cortex processor that I mentioned in the beginning, which we use to acquire, process, and downlink all the experiment information. So all the commissioning log files, images, etc., as well as the software-defined radio and the high-definition camera. So here you can see an image that we acquired from the HD camera, which is picturing the north of Svalbard. You can see a close-up of this glacier right here. We have a resolution of about 50 meters per pixel, so it's right in the sweet spot for Earth observation, cloud detection, and pattern analysis. And here is another animation that was made, as you can see, where we are orbiting, acquiring images as we are. We also got some preliminary results from the software-defined radio. So again, as you can see here, as a result of commissioning, we end up with files simply on the Linux file system that we can download via S-band, and we plotted these files in Spectrum, as you can see, and this is a recording where one of our UHF stations uplinked a carrier. And that we could see basically the Doppler shift here in this very short recording. These measurements were also performed at different gains, as you can see in the file names here, so that we can get a sense of appropriate gain settings to use in orbit. All right, so about our amateur radio outreach. Prior to launch, we initiated a worldwide call for the radio amateur community to start listening for OPSAT. Being a radio amateur operator myself, we exactly knew how to address the community and to get in contact with the right people. And in about a week, the news was spread to almost every amateur radio community out there, which resulted in basically amateur radio operators on every continent listening out for OPSAT, which was excellent. This, of course, all resulted in the fact that beacons were received and decoded, confirming the spacecraft was healthy even before we made contact with the spacecraft. So even before that, we already knew that the satellite was healthy and that the antennas had deployed and that beacons were being transmitted. On top of that, we also coordinated early on with the SatNOx team for early entry of OPSAT, so that also radio amateurs which were operating a SatNOx ground station were all set up to track OPSATs and provide early data to the flight control team. And in the end, we also provided certificates for those who participated in the Catch the OPSAT competition, which was also welcomed by the community. All right, as a conclusion, the early operations were carried out on UHF because we had an early S-band safety issue, which was fortunately quickly solved by an onboard software update that was carried out in orbit. To summarize, GNU Radio was crucial for a UHF ground segment. It's still crucial. We use it for day-to-day operations. It led to our first beacon report after separation by radio amateurs. Even before we made contact with the spacecraft, it played an important role, obviously, in the LEOP, the launch and early operations phase. It also made the amateur radio outreach possible because it was the perfect way to show the community how to decode OPSAT, how to get familiar with the link protocols, etc. An ESA lessons learned that was literally taken from our mission manager, which says that radio amateur support was essential to our mission success. If an ESA mission is using those frequencies, then it is essential to prepare and involve that community and basically stick to their rules in order to fully benefit from that support. So with that, the flight control team would like to thank the amateur radio and GNU Radio project communities for their support and ongoing development. And finally, I'm ending with this slide, the outlook. So we're close to the beginning of the experimental phase, where validation of experiments will take place on the satellite engineering model before we uplink them to the spacecraft. Afterwards, they're executed and we disseminate the results to the experimenter. We have a lot of external experiments, again, as I mentioned in the beginning, through the startups, from startups to large space and defense corporations, but also a number of internal experiments by ESA. And in the end, we're also planning, well, during the mission, we're also planning amateur radio experiments or the UHF link, potentially image dissemination and RF uplink experiments. So with that, I would like to thank you for your attention. And if you want to get in touch or have any additional questions, you can post them, or you can contact us, contact me on my email or the mission manager, David Evans. Here are also the links to the GitHub repository, as well as the ESA OPSAT page, and also finally our amateur radio information bulletin, where we regularly post news for the amateur radio community. So thank you for your attention. And that's it from my side.